In the last section, we covered the definition of the 6 basic trig functions, and in section 1.4, we're going to continue using other things with the definition. We alluded to some of this in the last section already, so some of this we already discussed. But first, let's talk about identities. So the definition of an identity, identities are equations that are true for all values of the variables for which all expressions are defined. Right? So first you have an equation with a variable in it. You plug any number into everywhere there's a variable, you plug in a number. If the equation turns out to be true no matter what you plug in, or if you get undefined, then if you get undefined, we don't hold it against the identity. We still say it's an identity. But every value you plug in and you get a number equals a number, the two numbers have to be the same. Just to do some examples, so the next question says, determine whether or not each of the following 3 equations are identities. So the first one is x plus 5 is 5 plus x. So if you pick your favorite real number and plug it in for x here and plug it in for x here, will these two, both sides of the equation be equal? Okay, is that true for every number? So if you pick any number and put it here and here, is that number plus 5 plus x? Of course it is, right? This is we're using the commutative property of addition of real numbers here. We know x, anything plus 5 is 5 plus anything for any real number x. So this is an identity. Check. Okay. Now what about this equation? X squared plus 2 equals x plus 1. Right? So this is an equation. If you plug any number in for x, will both sides of the equation here be equal? This is certainly defined, right? The issue about being undefined didn't apply in the first equation or in this one. So are these always equal no matter what you plug in for x? Well, the answer is no. For example, if I plug in x equals 0, you get 0 squared plus 2. That side, the left-hand side, is equal to 2. If I plug in 0 for x on the right-hand side, you get negative 1. And 2 isn't negative 1. So this is not an identity. Right. To show an equation that's not an identity, all you have to find is one value that when you plug in for x, makes the equation not true. Now, that begs the question here, right? This is not an identity, right? So not every x value makes this equation true. What's an obvious question? For which values of x would the equation be true? And notice that's solving an equation, right? So this is not an identity. If you have an identity, there's nothing to solve. Everything works. Here, not everything works, so an obvious question is what does make this equation true? And so you'd solve the equation. Now what about this last one? X equals x squared over x. So if you plug in your favorite number for x, will this side equal this side? Now something we have to look at are where is this equation undefined? Where are values undefined? Notice if you plug in x equals 0, 0 squared divided by 0 doesn't make any sense, right? You can never, ever divide by 0. 0 over 0 is undefined, right? But again, the definition says these two have to be equal when all the expressions are defined. So even though 0 doesn't work here, we get undefined, we don't hold it against it. It could still be an identity. So for any number besides 0, if you plug it in for here and here and here, will these two sides be the same? And the answer is yes. So this is an identity. 5 squared divided by 5 is 5. Negative 7 squared, negative 7 quantity squared divided by negative 7 is negative 7. Okay, so for any number besides 0, these two values will be the same. So even though 0 makes the right-hand side undefined, we don't hold it against it. Okay, so we're interested in identities in this section. And so the first ones are the reciprocal identities, which I mentioned in the last section. So they're in your notes. I wrote them down here. Sine is 1 divided by cosecant. Cosecant is 1 divided by sine. Yeah, don't memorize these. What are these first two identities saying? Sine and cosecant are reciprocals of one another. When you take 1 over a number, that's taking the reciprocal, right? If I give you 2 and say take the reciprocal is a half. If I give you 7/8 and say take the reciprocal, that's 1 over 7/8. But how do you divide by a fraction? You invert and multiply, that's 8/7, right? So the reciprocal is 1 over something. Okay? And notice what the next two identities, reciprocal identities, are saying. Cosine and secant are reciprocals of one another. Tan and cotan are reciprocals of one another. So I mentioned that in the last section. don't memorize these, just remember as pairs. Sine and cosecant of reciprocals, cosine and secant of reciprocals, tangent and cotangent of reciprocals. Okay? Now two we haven't discussed, which are new. Tangent is sine divided by cosine, cotangent's cosine over sine. If you can just remember one of these, you get the other one for free. I know tangent of theta is sine theta over cosine theta. I know cotan is a reciprocal of tan. So if I know tan is sine over cosine, cotan is a reciprocal cosine over sine. So if you can remember one of these, you get the other by reciprocals. So you have to know these, and if you know one of these, you get the other for free. Okay, so now we have these next three are called the Pythagorean identities, and students always say, why are they Pythagorean identities? Because think about it, right? Like in the last section we had 3 squared plus 4 squared is 5 squared, the three sides of the triangle, 3, 4, 5. Notice the form here, something squared plus something squared is 1 squared. 1 squared plus something squared is something squared. They all have the same sort of form, something squared plus something squared is something squared. Okay, let me try to convince you of this first one. I want to convince you that sine squared theta plus cosine squared theta is always equal to 1. And we're going to do this in chapter 5, proving identities are true. The procedure is start on one side and do things to it that you know and work your way to the other. So I'm going to prove this one here. So I'm going to start with sine squared theta plus cosine squared theta. I'm not going to write equals 1. I don't know that it's equal to 1 yet. I want to show you that. Okay, well, what's sine of theta? Okay, I'm going to write that in terms of x, y's, and r's. What was sine of theta in terms of x, y's, and r's? Sine of theta was y over r. So sine is y over r, sine of theta, and cosine of theta is x over r. Okay, so I'm just going back to x, y's, and r's. Well, how do you square a fraction, right? So this is sine of theta squared. Well, that's y over r times y over r, and to multiply fractions, you multiply across. Y over r times y over r is y squared over r squared, and x over r times x over r is x squared over r squared. And now I have a common denominator. To add fractions, you need a common denominator, which I already have. So to add fractions with the common denominator, you keep the common denominator and you add the numerator. The numerator is y squared plus x squared. Now that's not really looking like 1. Remember, we're trying to get to 1. But remember our picture, our XYR picture, the triangle picture. We had x and we had y and we had r. What was the relationship between x, y, and r? Pythagorean theorem, Pythagorean identities. X squared plus y squared is r squared. So I can replace the numerator, x squared plus y squared, with r squared. Now remember, r is never 0. We always assume we picked a point on the terminal side, not at the origin. So r is greater than 0. So it's not 0 over 0. What's r squared divided by itself? 1. So I started on the left-hand side and did algebra to it and got to the right-hand side. So sine squared theta plus cosine squared theta is always 1. I mean, if you want, pause the video, pick your favorite value for theta, and plug it in, right? So, for example, type in sine squared of 20 degrees plus cosine squared of 20 degrees. Type that in the calculator. Now remember, when you type that in, you have to type it in as sine of 20 degrees squared plus cosine 20 degrees squared. Type that in, you're going to get 1. Now remember, the angle here and here have to be the same. You can't put 20 degrees here and 50 degrees here. The theta has to be the same. Okay, so you can do that. Pick a couple of values and do that and show that you get 1. Okay, so the next example says, let's convince ourselves the second Pythagorean identity here is true. 1 plus tangent squared theta is secant squared theta. Now I'm going to do this a different way. I could have done it. I could do this exactly the way I did the last one. Write 1 plus tangent squared theta, replace it with x, y's, and r's, and then do algebra to get to secant squared. I could do it the same way, but I already did one like that. I'm going to do this one a different way. I already know sine squared theta plus cosine squared theta is equal to 1. We know that's true because we just proved it. Okay? Well, if this is equal to this, I could divide both sides by the same thing and get another valid identity. So in particular, I'm going to divide both sides by cosine squared theta. So I'm starting with that, and I'm going to divide both sides of this equation by cosine squared theta. Right? if this is equal to 1, that divided by cosine squared is 1 over cosine squared. That's a new identity. That's what we're going to do a lot in this course, is have an identity you know and then make a new identity from it. So I'm starting with an identity we know, and I'm going to use that to get a new identity. Well, I'm basically going to do what I did before backwards, the steps I did. So notice we wound up adding fractions in the last example. Here I'm going to split them up. So this is something plus something over common denominator. I'm going to break that up. Sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. And I'm not going to do anything to that side. Okay, so in the last example, we added fractions to get to here. I'm breaking them up. Okay, I've run out of room. Let me come up here. Okay. Well, and remember what I had before. I had x over r squared. We went to x squared over r squared. Now I'm going to go backwards. I have something squared over something squared. That's the same thing as sine theta over cosine theta squared, isn't it? Right, so I'm basically doing what I did before backwards. Cosine squared over cosine squared is 1. And 1 over cosine squared is the same thing as 1 over cosine theta squared, right? Because 1 squared is 1 and cosine squared is cosine squared. And we really only have one step to go now. Right? Well, what's sine theta over cosine theta? That's one of our quotient identities. Sine theta over cosine theta is tangent theta. So this is tan theta squared plus 1. And then 1 over cosine, that's saying what's the reciprocal of cosine? Right? 1 over cosine is secant. And don't forget we're squaring it. So there's our second one. So I proved the first one way, and I got the second one from the first one. Now how do you think we get the third one from the first one? Instead of dividing everything by cosine squared here, do the exact same procedure, but divide by sine squared here and sine squared here, you'll get the third Pythagorean identity. What's nice is, if you can remember the second one, 1 plus tan squared theta is secant squared theta, say that the same thing again with a co in front of the two trig functions, you get the third one. 1 plus cotangent squared theta is cosecant squared theta. So if you can remember the first one and the second one, you get the third one from the second one, but by just adding the word co. Okay, so we've convinced ourselves that those are true. And so the next example says we want to use some of these. I'm going to leave all these identities up here in case we need them, even though you have them in the notes. And it says, use the reciprocal and quotient identities to find all 6 trig function values for theta equals 630 degrees. Now we did problems like this in the last section. Okay, so I'm going to do this a certain way, and then always do these this way from here on out. I'm not going to do it the way we did in the previous section. Right, so what I'm getting at here, now let's draw a picture of 630 degrees. The first question I always ask myself when I'm sketching an angle, is this more than once around? Yes, it is, right? That's more than 360 degrees. So 630 minus 360 is 270 degrees. So if I go all the way around 360, right? How much more did I have to go? I still have 270 to go. So 270 more puts me here. So there's a picture of 630 degrees. It's 360 plus 270. And notice what type of angle this is. This is a quadrantal angle. I stopped, the terminal side stopped on the negative y-axis. Okay, so this is a quadrantal angle. So quadrantal angles do not involve triangle pictures. Okay, now we did a problem like this in the last section, right? You pick a point on the terminal side, and I was picking like 0, 0, 5, and -4, 0, so -0, -10, or something like that. Okay, but I'm gonna use the unit circle here. If you've had trig before, and I'm finally gonna use the unit circle. So I'm going to pick the point that's 1 unit away from the origin. Right, so what point is 1 unit away from the origin on the negative y-axis? That's 0, -1. Okay, so from here on out, when I do any quadrantal angle like this, I'm going to pick the point 1 unit away. So I'm never going to pick 0, 5 or -4, 0 ever again. I'm always going to pick the point 1 unit away. So which points am I always going to pick? 1, 0, 0, 1, minus 1, 0, 0, minus 1. From here on out, when I do trig function values of a quadrantal angle, I'm always going to pick one of those 4 points. So never, 7, 0, 0, negative 12, negative a million, 0. No. I'm always going to pick the point 1 unit away, because that makes a unit circle, right? Circle of radius 1. That's what I'm doing here, for those of you that have seen trig before. Now, why am I picking the point 1 unit away? I need to explain why I'm doing this. Remember, sine of an angle, right? Sine of an angle was y over r, and cosine of an angle was x over r. So if you pick the point 1 unit away, what's r going to be, right? So if you're on the unit circle, what I just had, if I'm on the unit circle here, even though I'm really focusing on these 4 points here, right? If you're on the unit circle, what's r? R is 1. So if you pick a point on the unit circle, r is 1, and so this turns out to be y over 1, which is y. This turns out to be x over 1, which is x. So how do you get the sine of an angle when the point on the terminal side is on an axis? It's just the y value. And the cosine is just the x value. It makes things a whole lot simpler. Now, if I have an angle here, just in the middle of the quadrant, not on the axis, suppose I give you 10 degrees here. So imagine the unit circle here. What are the coordinates of that point? It's some x, y. I know x is the cosine and y is the sine, but can you tell me what the coordinates are of that point? No. I mean, I have no idea what they are, right? You can't tell what that is. That's 1, but what's x and what's y, right? You have no idea, right? But notice for a quadrantal, if I tell you that's 1 away, that's a point 1, 0. That's a point 0, 1. That's a point minus 1, 0. That's 0, minus 1. So for the quadrantals, it's easy to tell me what the coordinates are. If it's not a quadrantal, that's r is 1, but what are x and y? Who knows? Okay, so I'm only going to use the unit circle when I do quadrantals. Okay, so from this, I'm blowing this way up. I'm trying to explain why I'm doing what I'm doing here. If you pick a point on the terminal side of an angle, 1 unit away from the origin, the x value is the cosine, and the y value is the sine. Easy. Okay, so from here, I know that sine of 630 is negative 1. I know cosine of 630 is 0, right? Cosine's the x value, sine's the y value. Easy. I really don't even need the picture. Okay, so once I have sine and cosine, I can get the other 4 trig function values by reciprocals and quotients, right? So in the last section, I found sine, cosine, tangent, and used reciprocals to find the other 3. But here, how do you get tangent? Right? Our quotient identity says tangent, sine divided by cosine. Sine over cosine, negative 1 over 0 is undefined. So now, once you have sine and cosine with all these identities, you can get all 6 trig functions. So what's cosecant going to be? Well, it's the reciprocal of negative 1, which is negative 1. What's the secant going to be? Secant's a reciprocal of 0. 1 over 0 is undefined. And cotan, now I don't like saying the reciprocal of undefined because that doesn't make any sense. But cotangent's cosine over sine. And cosine over sine is 0 over minus 1, which is 0. Very easy. So I really don't even need the picture to do these anymore. Just remember the 4, figure out the 4 points. Okay, so this isn't in the notes, but just for kicks. What if I said, let's do sine of 0 degrees and cosine of 0 degrees? So could you do those without, writing all this stuff down? Right? Where's 0 degrees, right? 0 degrees is here. There's no rotation, standard position. So what point am I using? I'm using the point 1, 0, 1 unit away. Cosine's the first number. Cosine of 0 is 1. Sine of 0 degrees is the second number, 0. And so tangent would be sine over cosine, which would also be 0. And then do reciprocals. Right? So what about, 180 degrees, which is what we did in the last section. 180 degrees is here. Cosine is negative 1, sine is 0. What about 90 degrees? Cosine is 0, sine is 1. Very easy. So I don't even really need the pictures. You can picture this in your head. Think about what the coordinates are. Cosine's the x value, sine's the y value. So it's really not that hard. Now, again, that's what I'm going to do for quadrantals from here on out. I'm always going to pick the point 1 unit away from the origin. Cosine will be the x value, sine will be the y value. Now this next little fact, this is our last fact before we start working problems. It's called the ranges of the trigonometric functions. Remember, when you have a function, the domain are all the values that you can plug in for x, range are all the values that the function can spit out for y. Okay? Just because you have a function, for example, f of x is x squared, if I'm mapping real numbers to real numbers, the domain is all real numbers. I can plug in any value for x and square it and get an answer, but what's the range? What are all the possible y values you can get? Notice you can't get y as a negative number, because if you square a real number, you can't get negative 2.5, say. Right? So the domain here is all reals, because you can plug in anything and get an answer, but the range are all the, I was going to say positive, which isn't true. When you plug in 0, you get 0, so it's the non-negative real numbers. Okay? So range are all the y values you can get. Okay. Okay, so let's talk about the trig functions here. It says sine of theta, when you so theta is your domain. You plug in numbers in the domain for theta, for the angle. When you take sine of it, you always get an answer between -1 and 1 inclusive, same for cosine. What about tan and cotan? Tan theta and cotan theta can be any real number. I'll explain why. And lastly, secant theta is either less than or equal to -1 or it's bigger than or equal to 1, and same for cosine. I'll explain all these in a second. Okay, so why is this true? I don't think I need these anymore. Okay, let me go back to my triangle picture. Let's talk about sine and cosine here. All right, let's go back to my triangle picture. We had, if that's theta, we had x and y and r. Think about what the definition of sine. Sine was y over r. In a right triangle, this side, the opposite side, y, is always going to be smaller than the r. So when you do sine of theta and you get y over r, y is always less than r, and so that will be less than 1. Okay? Now, it's never going to be equal to 1, so why do I have the equal here? Well, we just saw, for the quadrantals, you can get an equal. So for the triangle picture, you're never going to get plus or minus 1 for sine and cosine. For the quadrantals, notice, see, you can get pluses and minus 1s. And same for cosine. Cosine's x over r. In the triangle picture, x is always strictly less than r. So x over r, when you divide, will be less than 1. And when can x and r be the same? When you have a quadrantal. Now, what about the negative? I mean, I drew this in the first quadrant. If you're in the second quadrant, x could be negative, right? So you could have like -4/7. So then that divided by that number is always, the absolute value of that number is strictly less than that. And so you'll get -4/7. So that's why it's between plus or minus 1, because you can get negative values in other quadrants. Okay, now what about tan and cotan can be any number? That's kind of interesting. So when you take sine of an angle or cosine of an angle, your answer's trapped between -1 and 1 inclusive. But tan and cotan can be anything. Now why is that? Well, let's just pick a number for, right? Let's convince ourselves we can get tangent to be 8.2. I'm just making up a number to show you that you could do this anyway, anytime you want. Okay, think of that as 8.2 over 1, which is still 8.2. And remember, tangent is the opposite side over the adjacent side. So could you draw a triangle where the opposite side is 8.2 and the adjacent side is 1? Sure. Right? Suppose I drew something like this. Make that length 8.2, make that be 1, right? 1, 8.2. You could draw that. That's the point 1, 8.2. No problem. And if this is my angle theta, what's the tangent? That over that, 8.2. So the 8.2 is not special, right? Pick your favorite number here. Put that number here, put that number here, and tangent will be that number over 1. Same for cotan. Cotan is that side over that side. Sorry, that side over that side. So you just, if I want 8.2, put 8.2 here and 1 there. So you can get any number you want with tan or cotan. And how do you get all the negatives? Put them in the other quadrants. And then what the sides will be negative. Okay, so that's why tan and cotan can be anything. Now what about secant and cosecant? Well, this sort of makes sense. I remember these with a number line, to be honest with you. Right? We just said sine theta and cosine theta are trapped between minus 1 and 1, right? So anything from here to here. And again, we're not just talking about the world of integers. We're talking about 7/8 and -5/6 and 99 over 100, right? We're just not, it's not -1, 0, and 1. Those are not the only possibilities there. Now let's think about this for a second. Sine, we know sine could be, I'm making up a number here, 7/8. Okay? There's an angle where sine is 7/8. Well, if sine of theta is 7/8, what's cosecant of theta? Well, sine and cosecant are reciprocals of one another, so cosecant of that same angle will be 8/7. And notice this number is bigger than 1. 8/7 is 1/7. So notice cosecant is going to be out here. It's bigger than 1. And now what if sine were -7/8? And cosecant would be the reciprocal, which would be -8/7, which is out here. Now could cosecant be 1 or -1? Well, we just learned sine could be 1, right, on the quadrantals. Well, what would, if sine of theta is 1, what's cosecant of that same angle? The reciprocal of 1 is 1. So cosecant can also be 0, can also be 1. Okay? Now what if, same thing, we know sine could be -1 on a quadrantal, cosecant could also be -1. There. Right? And so cosecant's here and here, including 1 and -1. Same for secant. Right? If I change this to cosine and secant, it's the same argument. Okay, so I just remember this picture. Sine, remember, I'm not talking about theta, I'm talking about once you take sine of theta, you get an answer between plus or minus 1, including plus or minus 1. If you take secant or cosecant of an angle, you get 1 and bigger or -1 and smaller. So you don't have to memorize that, right? Just think of the picture, right? Sine and cosine give you answers here, secant, cosecant are here. And I didn't put tan or cotan because that could be anything. Okay, so that's kind of the theory in the section. Let's work some problems now using this theory. So the first problem says, suppose tan of theta is -1/5, find cotan theta. Well, this is a reciprocal, right? Tan theta and cotan theta are reciprocals of one another. So if tan theta is -1/5, cotan theta is -5, right? Just the reciprocal. There's nothing to that. The next problem says, suppose cosecant theta is 1.42716,321. Okay, 1.42716,321, and it says find sine theta. Well, what's the relationship between cosecant theta and sine theta? They are reciprocals of one another. So the reciprocal, that's 1 over 1.42716,321. But we probably want to write it in the same form. 1 divided by 1.42716,321 is 0.700690708. Notice cosecant was bigger than 1, right? Which it has to be. And notice when we found sine, sine was between -1 and 1. Okay, so that works out. Okay, this next number, 105. So this is solving a trig equation. This is our first time we've ever done this. It says find a solution for the equation. Tan of 3 theta minus 4 is 1 over cotan of 5 theta minus 8. Now notice it didn't say solve the equation, because solving the equation says find every solution in the world. There's an infinite number of solutions to this, so they made it easy. They said find one, just find one solution. Okay, so in this course, when we're trying to solve trig equations, well, first of all, what makes something a trig equation? We should talk about that. Remember, different equations have different names. For example, in college algebra, if you had 3x plus 5, not 3, 3x plus 5 is 7x minus 10, what type of equation do we call it? We call it a linear equation because both of the x's were raised to the first power and everything else were just real numbers. Right? And you learned how to solve linear. First you recognize the linear equations, and then you said, well, how do I solve those? Put all the x's on one side, everything else on the other, blah, 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 okay? And then later you did things like x squared plus 5x equals 7x plus 2. Well, this was a quadratic equation because the highest power in the x was the integer 2. and the other ones just had integer form. So that's a quadratic equation. And what methods did you learn? Put everything on one side and set equal to 0. You could try to factor, you could use quadratic formula, you could do completing the square, that sort of. You had different methods for that. Not the same procedure as with linear equations. Right? So what makes something a trig equation? Well, you have a trig function in it, and the variable is part of the angle. Okay? So see, if I had x plus tan of 20 degrees is 17, this is not a trig equation. Tan of 20 degrees is a number. You'd have x plus a number is a number. This is a linear equation. The variable's here, right? X to the first. So just having a trig function in your equation doesn't make it a trig equation. What makes something a trig equation? The variable is in the angle, right? So tan x plus 7 equals 15. This is a trig equation because the variable is part of the angle. Okay. So that's what I have here. Notice I have a trig equation. The variable is part of the angle. The angle here is 3 theta minus 4. It's all the other angle is 5 theta minus 8. Notice the variable showing up in both. This is a trig equation. Okay, so in solving a trig equation, you want to work it down to one of two things in this course. Work it down to trig function equals trig function, or trig function equals a number. Okay, that's the short-term goal with most of the problems in this book with solving trig equations. Work it down to trig function equals trig function, or trig function equals a number. Notice I don't have that here. I have trig function, tan of an angle, is 1 over a trig function of an angle. Okay, so this is not in one of the two forms I just mentioned. But how could we make it look like that? This is trig function, tan of an angle, but this isn't in that form. But we can rewrite that right-hand side, can't we? Well, this is saying 1 over cotan. This is the reciprocal of cotan. We know that 1 over cotan theta is tan of theta. The reciprocal of cotan is tan. Notice the angle stays the same, right? Whatever angle is here goes here. You don't take 1 over 5 theta minus 8. No, no, no. 1 over the cotangent of an angle is tan of the same angle. The angle stays the same. Notice I have trig function equals trig function. Okay, so that was the goal here. You want to get trig function equals trig function, or trig function equals a number. That's the goal. Okay, so how can we solve this? Remember, it said find one solution. It didn't say find all of them. When could tan of one angle be tan of another? Right? When could tangent of one angle be tangent of another? One situation where that could be true is if this angle and this angle were the same. Wouldn't tan of, I'm just making something up, wouldn't tan of 15 degrees be tan of 15 degrees? Right? We saw before, coterminal angles are going to have the same trig function value, so they don't have to be equal. They don't have to be the same angle, right? Tan of 0 degrees is the same as tan of 360 degrees, right? Because 0 degrees is here and 360 degrees is here, so they have the same terminal side, right? So they don't have to be the same angle, but in this problem it just said find one solution. So a solution will be when the two angles are the same. Now that's because the trig function's here with us. If this had been sine and sine, I still would have set the angles equal to each other. Okay, now what type of equation do I have? Now I have a linear equation. Notice I did not cancel the tans. That's not what I did, right? This is not multiplication. It's not tan times. It's tangent of. So I'm using the argument tan of one angle is tan of another. When could that be true if the angles are the same? Okay, that's what I did. I didn't do algebra to go from here to here. I just used some logic. Well, let's solve, right? This is a linear equation. Put all the thetas on one side. Let me subtract 3 theta from both sides. And then add 8 to both sides. And then divide both sides by 2. And again, when I'm doing equation solving, you don't have to write the degree signs, but at the end you should. So theta is 2 degrees. Notice when theta is 2, you get tan of 2 degrees is tan of 2 degrees, which would be true. So notice that is a solution. It's not all the solutions, it's a solution. Okay, let me stop here and do a part 2 for this section.